And thank you very much for the invitation to speak here. It's a huge pleasure. So my talk has really two parts. First, I want to present what is the Borel-Ecalle resummation methods in quite some details, because I don't think it's a very common topic yet. And those are the first two sections. And then I want to illustrate how to use this resummation method on a quantum field theory problem, namely a Wess-Zumino model. Okay, so I think it's quite common in physics that we don't know how to solve the problem we want to solve. So instead we do a perturbative approach on some small parameter. And in quantum field theory, the small parameter is typically the fine structure constant of your theory, and the nth term of your perturbation series is given by a finite sum of Feynman graphs, which of course have them to be renormalized and everything. Those coefficients, they will typically depend on some kinematical parameters, which I will consider fixed so that I can see everything as a formal series. So, because typically this perturbation series does not converge. All right, and to be a bit more precise, I will not write on any observables that you can imagine in quantum field theory, but I will really focus on the 2-point functions. So this perturbative approach, it's extremely successful, of course, and some of the most remarkable results of quantum field theory have been obtained via this approach. But you might also not be completely happy about it. One possible argument is that it's hard, sadly, in that I think we know how to compute up to order, in the nicest case, up to order 10, 11, maybe 12, but quite soon we cannot do anything anymore. The number of graphs explodes completely. Another problem, maybe more fundamental, is that there are regimes in which the perturbative approach is not very efficient. In particular in quantum field theory, of course, where your perturbation parameter becomes of order 1, so that the nth plus 1 term is on the same order than the nth term. So going further in the perturbation series doesn't give you so many new informations. Another problem, which for me is more philosophical, is that this perturbation series is not convergent. It's also, we will see in a moment, typically not Borel summable. And so it's a bit unpleasant philosophically speaking, because if this object you try to compute, you like to see him as having some nice physical meaning, I'd also like to have it as a nice mathematical object of functions and not formal series which I cannot evaluate at any place but 0. So from those observations, you can ask a bunch of questions, and two questions I want to talk about today are: first, can we reach some non-perturbative data from this perturbative series, and can we give a meaning to this formal series, at least in a quantum field theory case? Right. Right now, let me focus on the first questions, and to be a bit more specific, to precise what I want to say. By non-perturbative, I mean something that cannot be seen at any order in the perturbation theory. So you can go as far as you want in the perturbation theory. If you have infinite computational power, there are some things that you will always miss. And if you see the perturbation theory as a Taylor expansion of something, it might be that these true things that you are expanding have components that are non-zero but have a vanishing Taylor development. And a truly marvelous fact, in my opinion, is that the perturbative series actually know about non-perturbative information of your theories. And this can be reached in many ways, I'm sure, but one possible way is through resurgence, is the so-called truncated approach. The idea being to say that your perturbative series G is actually only a part of a bigger object, which is a truncated, which has this form. The term n equals 0 is your initial perturbative series. For each n is an instantonic sector, we call it n instanton. And each of these phi n is a perturbative series, which a priori is a formal series. Okay. Before I go further, one remark: this is a very naive and unwavering argument. I'm not pretending that this is a general case, that I'm really telling you how to do this approach. It's just the very basic idea. So this is done by quite a few people. Let me quote Schiappa and Aniceto, which I think were among the first to start this project. Also Marc Belon, my former PhD advisor, Dune, Costin, and many, many others. It's a very active area of research. Now, the key point is that those big phi n, you can actually obtain them from your initial perturbative series using the whole machinery that in particular Ecalle has developed called alien calculus, median resummation, and other parts of Resurgent theories. The philosophy of how to get those objects is that they are actually encoded into the asymptotics behavior of your perturbative series. So the perturbation series started from this information in its asymptotics, perturbation of its asymptotics, and in more involved case, asymptotics of asymptotics, and so on and so forth. So this is very nice approach, I think, because it tells you even if A becomes a bit bigger, instead of computing just the first 10 order in the perturbation series, you can also compute some order in the instantonic sectors, and that will improve your approximation of the true object that is supposed to exist. But it's not quite what I want to talk about today, to be honest. I really want to focus on the second questions, how to give a meaning to this formal series. So my goal, very precisely said, is from this formal series that is a two-point function of a QFT, I want to associate a real honest functions that is holomorphic in some open domain in the complex plane. And the method with which I want to do that is the so-called Borel-Ecalle resummation method. So what is this beast? Well, it's a generalization of something very traditional called the Borel-Laplace resummation method. So let me start with that. The Borel-Laplace, as its name suggests, has two parts, Borel first and then Laplace. So the Borel transform is a linear map between two algebra of format series that maps point-like product of format series to a convolution product of format series. I'm using here the math convention that instead of writing it as a formal series in A around 0, I write it as a formal series around infinity. So think of Z as 1 over A. It tends to make computation a bit simpler. I also assume that my initial formal series does not have a constant term. I can put a constant term there. It's not a real restriction. Again, you need a bit more time to present that, but it's just a technicality. It also shifts the order by 1, which makes your formula simpler. But the crucial part is that the term, the summand of your format series is divided by n factorial. So of course, if your initial format series is reasonable, does not diverge faster than exponential, its Borel transform will be convergent in the neighborhood of 0. Before I precise a bit this idea, let me say a word about this convolution project. So the convolution product of format series is written below. Okay. What is really interesting is that if we are in the convergence domain of f hat and j hat, then the convolution product becomes a honest and nice convolution given in terms of an integral. So it's really a convolution product as we are used to it for functions, not only for formal series. I already pointed out that your Borel transform is convergent in the neighborhood of 0 if your initial formal series does not diverge too fast. And to be a bit more precise, it has to not diverge faster than a geometric series times a factorial. And it's not a very hard theorem to see that the Borel transform converge in the neighborhood of 0 if and only if f tilde is 1 Givray, has this type of bond. In practice, I will only deal with 1 Givray series, and I will not in the following say that I assume that my series are 1 Givray. Okay, so we have this transform, which is has very nice properties. In many cases, many series that you really want to resum, it does associate it to it real function, something analytic in some open around 0. It also is an algebra morphism. So in some sense, if you start from a problem that is nonlinear and you map it to the Borel plane, your Borel transform will solve the same type of problem with convolution products, but information survives. But so far, I'm not really moving toward the resummation, finding the resummation. And I'm going to do it by, thanks to the existence of an inverse Borel transform, which is the Laplace transform. So the Laplace transform is defined by an integral from the origin of the complex plane to infinity in the direction theta. So this symbol means that I integrate along the straight line from the origin to infinity in the ray theta. So the question is, when is this thing well defined as an honest integral of functions? Well, first I need that phi hat is a function, so that means at least somewhere. So I need that phi tilde is 1g ray. Okay. Also, I need it to be a functions everywhere, not, I mean, in the line, in the direction in which I want to integrate. So I need to have an analytic continuation in an open that contains the ray from 0 to infinity. And finally, I need this integral to converge, meaning that f hat has to be bounded by an exponential. We say that there's sub-exponential behavior. Now, if those three conditions are hold, then I define the resummation operator in the direction theta as the Borel transformation and then Laplace transformation. The fact that it depends on the direction is very important and actually leads to a lot of extremely interesting phenomena, like the sectorial resummation when you vary the angle. Also, you have the stock phenomenon when you cross some singular lines, and that makes the various sectorial resummation not be the same. It's extremely interesting. But once again, it's not really something I'm going to focus on because I'm trying to solve a physical problem. And in a physical problem, the direction in which you want to resum is given by your problem. Typically, I will have to take theta equals 0 if my perturbation parameter is real, if positive real. There might be other problem where I have to take pi over 2 or minus pi over 2. It doesn't really, it's not, or 3 pi over 2. It's not very important. But I cannot just say, okay, I cannot resum in this direction, so I will resum in another one, because then I'm just not solving my problem. So,
could you comment on the dependence on theta?
So, okay, if everything hold in, if you have two theta, so let's say theta 1, theta 2, and these three conditions hold between every theta in this arc, between theta 1 and theta 2, then the resummation that you obtain, the function that you obtain via these methods, their analysis domain, they intersect and they are analytic continuation of each other. So what happens, and that's called the sectorial resummation. And what happens is that when you hit a singular direction, so you can resum up to some direction theta singular, on which the analytic continuation does not exist, typically because you have singularities in this direction, then there will be a jump in those continuations, and that's called the Stokes phenomenon. And those jumps are really important and encodes a lot of important things, and it is an active field of research. It's just not really what I want to do, because I want to resum in one, typically in one of those singular directions. That's actually a sad fact of life, that if you start with a perturbative series in a physical problem, the direction in which you want to resum is typically singular. So the question is, why can this processus does not work in physical situations for perturbation theory? Well, there are, even if you have a 1G ray series, there are two things that can go wrong at least. One, very simply, is that f hat goes too fast at infinity, so that the integral does not converge. There is an aspect of Eccal's resurgence theory that deals with that, an extension of what I'm going to talk about called axial summation. With Mark, we have an argument that it's actually needed. It's a very important physical theory, but it will not be needed for the theory I'm going to talk about, so I will not do more than mentioning it. Another typical thing that can happen is that you don't have an analytic continuation in the direction of theta because you hit some singularities. The idea of Eccale is to say, okay, I will hit some singularities, but in many cases, the singularities are not so bad. In some sense, they are isolated. It's the crucial idea. And then Ecalle developed a concept for those functions that admit isolated singularities. He calls it resurgent functions, and the whole calculus to deal with those singularities, the alien calculus, but also a notion on how to avoid those singularities via well-behaved average. So that's what I want to talk about now. Let me try to define resurgent functions. You start with a set in the complex plane, which is non-empty, discrete, and closed, so that there is no accumulation points. And this set will be the set of possible singularities of your functions. You just define the resurgent functions as functions that admit singularities along any path that avoid this set. Let me recall that analytic continuation along a path means that you can cover this path by finitely many disks that overlaps, as in the picture. The picture is not from me. I think it's from Dorigloni's introduction to resurgence, one of the two good introductions to resurgence. So this, the idea is that you can cover, your function is well defined in the first disk and admits an analytic continuation in the second disk, which itself admits an analytic continuation in the third, and so on and so forth. So in some sense, it's better to see resurgent functions as functions from a Riemann surface that covers your complex planes with value in C. Another way to say it is that there are functions of homotopy of path with fixed endpoints in the set of C without omega. Okay, so those functions essentially tells you the possible set of singularities is not so bad. There will not be too many singularities. Typically, there will not be dense set of singularities, not arcs of singularities or something like that. Good. One remark is that this is not the most general approach of resurgence. Ecalle does have, Ecalle and Menu also does have an aspect of resurgence where the set of singularity can move, also can have one finite number of accumulation points, I think. But honestly, I am not aware of any situation in physics where we need this level of generality, and it's completely enough to deal with those fixed singularities. Okay. So this is a nice set of nice objects that have nice property, but what can we say about it? One very important theorem by Ecalle, but that Sauzin, in its introduction to resurgence and summability, gives a very explicit proof of it, is that the convolution product of omega resurgent functions is still a resurgent functions if and only if your set of singularity is stable under addition. And it's very easy to see that it's needed because takes the most simple, some of the most simple resurgent functions.
So sorry, the question, what does the notation C omega mean? I'm not sure what.
Where?
Omega.
Sorry, this one?
Yes.
It's Riemann surfaces above C where those functions live, because you can, in general, you have monodromy when you go around it. So they are not functions from C without omega. They live in some more complicated Riemann surfaces that cover C. You have to keep track on which sheets you go when you move in a complex plane. So those two meromorphic functions, of course, they admit analytic continuation along any path that avoid omega 1 and omega 2, because they are meromorphic functions. So they actually don't even depend on the path. And in their near the origin, you can compute their convolution product. It's a very easy exercise to prove that, that this is what you find with integral. And so those integral terms, they indeed admit analytic continuation along any path that avoid omega 1 and omega 2, but it's logarithm, so there you will have to keep track on which sheet of your Riemann surfaces you stay. But what's really important, you see that you have another term which has a pole in omega 1 plus omega 2. So this convolution product is not resurgent for the set big omega to be just omega 1 and omega 2, but it's resurgent for the set big omega equal omega 1, omega 2, and omega 1 plus omega 2. And this is an extremely general feature, that if you have two singularities and you take the convolution product will have singularities as the product that is the sum of those two singularities. So in order for these objects to be in the same resurgent set than the first two functions, you have to have that your set of singularities is stable under additions. And the hard part of this theorem is to show that this is actually enough. It's sufficient. So, okay, let's breathe 1 second and try to understand what we have so far. We have singular directions in which we want to resum. We say, okay, we are in a nice case where the direction is singular, but my functions does not have too many singularities, neither in this direction, neither in other direction that would cross, that would cut the singular direction somehow. So the singularities are not dense, okay. But that does not really tell me what to do, right? I still have the problem that when I want to do this Laplace transformation, I will hit those singularities, even if I know that there are not so many. And the second idea of Ecalle is to say, well, if you go toward a singularity and you're going to, well, you perform your Laplace integral and you're going to hit one of these singularity, you can just avoid it. You can deform your integration path going above or below the singularity and keep going after. And you can do that because you've defined those resurgent functions. That's precisely what you need to be able to do that, because you know that there is not other singularities too close, so you can deform your path of integration. Okay, very nice. So the idea of Ecalle is to say, since each singularity is actually not really a problem, but more of an ambiguity, you just sum over all the possible possible paths that avoid those singularities in the singular directions. To each of these paths, you attribute a weight. I use the convention that omega 1, omega n is the signature of my path, namely that each time I go on the left of a singularity, I take a plus. Each time I go on the right, I take a minus. So I hope the notations are fairly clear. Of course, you end up with the functions that does not depend on which sheet of the Riemann surface you are, since you have average over all the possible paths to all the possible sheet on which you can end up at the end. So this is a very natural, well, very clever idea, and somehow also very natural. That's really beautiful idea, I think. And then one caveat is that you cannot do anything. You have to have some autocoherence relations so that the object you define is actually well defined. Okay. But those coherence relations, they are fairly weak, and it's fairly easy to go home and create tens of average. So let me give you some examples. The most simple example, I think, is the lateral average. So for example, the left lateral average, you associate the weight 1 of the path that always avoids the singularity by going on the left of it, and 0 to every other possible path. Okay, it's a very boring average, but it is an average. And of course, you also have the right average, which we give the weight 1 of every path that goes to the right of your singularity. A more interesting average, and an average that is used by physicists, is called the median average. And this, well, physicists use something called median average, but that has an extremely different definitions. So the link between the two point of view is not so clear, actually. The idea is that to a path that goes p times on the left and q times on the right, you associate these coefficients. It's not a very hard exercise to check that this is actually an average. It satisfies the autocoherence relations. And those average, the lateral average and the median average, they belong to the same family of uniform average. That's where the U come from. They are uniform in the sense that two paths that which have the same length and will avoid the same times going on the left or going on the right will have the same weight. So it doesn't really depend on the path. It only depends on the number of plus and minus in the signature of the path. But you have other average, many others that are not in this family. And one example, a bit more complicated to define, so I don't want to spend time defining each terms, is the so-called Catalan average, which is given by Catalan numbers and the Catalan polynomial. And this one is not a uniform average. It's a family of average, actually. It depends on one integer parameter. And they are not uniform. Okay, so you have a lot of average, but of course, not all average will do the job that you want them to do, because what you want to do at the end is build a solution to some problem you started from, right? You are still trying to resum something. So you started from some problems you've solved in terms of formal series, and you want to resum this formal series, but you want the the resummation that you give to this formal series to solve the same problem. Otherwise, you just build an object that does not make any sense. So in particular, what do you need? Well, first, since the Borel transform and the Laplace transform are algebra morphism, you also need the average to be an algebra morphism. So that's the first property. Also, if you want to build the physical functions, it's good to have a real functions, meaning something that commute with taking the complex conjugate. And it's easy to see that if you have this, if you require that when you flip your path, you just take the mirror under the singular direction, then you just take a complex conjugate of the weights. Those two conditions, P1, P2, together, they are called the algebraic problem. So finding an average that obey P1 and P2 is the algebraic problem. The last things you want is that in a reasonable case, you want to be able to take the Laplace transform. And this is actually more subtle, because the question is, what is reasonable? What you could say is, well, if my resurgent functions admits an exponential bonds along any path that avoid those singularities, then I want the average to also have this type of exponential bonds. Okay, that would be reasonable. The problem is, even very nice functions that you really want to resum, they do not have this type of bonds along every path that avoids singularities. They just, because you have some path that will make your functions blow up completely, even if you start with something nice. And those are paths that typically cross the singular direction many times, like this. So what Ecalle tells you is that instead, it's enough. So if you just require that you are able to resum functions that are where every path has an exponential bond, in practice, you would not be able to resum many functions. So Ecalle gives you a more powerful tool by saying, I want that if my functions admit an exponential bond in the principal branch of the Riemann surfaces, that means the path where I always avoid the singularity by the same direction, whether on the left or whether on the right. If I have an exponential bond on this path, then the average should have the same type of path. And this is called the same type of bond. And this is called the analytic problem. So we have the notion of well-behaved average that solves the algebraic and the analytic problem. So the question is there well-behaved average? And it's not very easy. It's very easy to see that the lateral average solves the analytic problem, since there is only one path that contributes. Of course, the bonds will be preserved, but it completely fails to solve the algebraic problem. On the other hand, it's not easy to see that the median average solves the algebraic problem. This was actually claimed in an article by Ecalle and Menou, but I don't think they published that it was true, but it was really explicitly proven by Schiappa and Aniceto, I think in 2012, by using this other approach of average, where they really showed that it does solve exactly this algebraic problem. Ecalle and Menou also claimed that the median average does not solve the analytical problem. So since this is the average that physicists use, the median average, we can ask whether or not is that a problem. I am pretty convinced that it is not a problem. Because essentially it's used for the transitory approach to resurgence, not for Borel-Ecalle resummation. And I don't think it would change anything to change the average. but that's an interesting topic of conversation. And a difficult theorem due to Menu in his PhD thesis, I believe, in the early 90s, is that the Catalan average is actually a well-behaved average. There are other known examples of well-behaved average, but only finitely many, I think 6 or 7 families.
There is a question. Is there an example where the median average fails P3?
Fails what?
P3, the last...
I don't understand the question. If the person can...
so you can read it in the chat, but...
I need to stop the full thing. Oh yeah, sorry.
Otherwise, Daniela is welcome to unmute himself and ask a question.
Sorry, I should have done it before. So you said that the median average does not satisfy property number 3, so it's not gonna have, in general, exponential growth. Is there a concrete example where the median average does not have exponential growth?
Not that I'm aware of, because I don't think it's ever done this analytical bonds on the median average, with median average.
Because that average is the one we use the most as physicists.
Yeah, definitely. But I really don't think it's a problem, because okay, the Laplace transform is not might not be defined, but we are actually computing a transseries expansion, right? And I suspect that the transfer expansion is unique and doesn't depend on which average you're using, as long as it satisfies the algebraic properties. So I think that for computing the transfer expansion, it's completely fine.
Good, thank you.
There is also the chance that it does not work in the full generality, but it works in every case that is actually on which it actually used. It's a possibility.
Could you again show the definitions of P1, P2, P3?
Yeah, it's there. So this, the analytical property P3 is really to make sure that you can take the Laplace transform at the end. But physicists that use resurgence, I don't think they really prove convergence properties or existence of a solution. They compute the solutions and they compute it via a transseries approach. And I don't think that the transseries depends on which average you choose, as long as it satisfies P1 and P2, of course, for which the median average does. Also, I don't have a proof that the median average does not satisfy P3. It's just a claim in an article of Ecalle and Menu in the 90s. I don't think they've published their proof. Okay, so there exists well-behaved average, and let me summarize Borel-Ecalle resummation methods in one slide. It's done in 3 steps. You start from a formal series that solves some problem that you're interested in. You take a Borel transform on which you arrive to resurgent functions, so functions that admit an analytic continuation along any path that avoid singularities. You average in the singular directions on which you want to resum. At these steps, eventually you might have to do this so-called acceleration if behavior at infinity is not very good, but let's not worry too much about that. And finally, you take the Laplace transform. And you arrive into some really honest functions that are analytic in some open domain of C. So in practice, if you want to apply this method, you have 3 things to show. First, you need to show that your initial formal series is 1 Givray, so that your Borel transform is convergent in an open of 0. You have to show that it admits analytic continuation along every path that avoid the singularities, which is tough in general. And you also have to admit that those analytic continuation admits an exponential bond on the principal branch of the Riemann sheet C / omega. But if you manage to do that, then Borel-Ecalle tells you that for free, that you have a solution, which is a real function, so once again, that solves your initial problem, and which is given by the Laplace transform of the averaged Borel transform. So the big question is, can we do that? Because that's a method. It has been used for some mathematical problem, but can we use it on physical problem? Of course, I will try to convince you that yes, we can. At least in some in a nice quantum field theory model. And this nice quantum field theory model is a Wess-Zumino model. So
sorry, there is just a question by Domenico Monaco. Does this procedure give any information on the size of U?
Yes, completely explicitly. Actually, U is a disk that is tangent to the unity. There is a picture at the end where I show the size of U, and the size of U depends to the exponential bonds that you found there. It's a like for usual Laplace transform, the same type of results. But of course, the question is, did the bond that you found, is it optimal? Maybe there is a better bond that will make you have a bigger analyticity domain. So, okay, let's try to apply that on the Wess-Zumino model. This is an actually old quantum field theory model, which is massless and exactly supersymmetric. The fact that it's exactly supersymmetric, it makes this model to have no vertex renormalization. And that really simplifies your life. So this model has renormalization group equations where gamma is the anomalous dimension of your theory and is the first derivative of G with respect to L evaluated at L equals 0. And L is the logarithm of the impulsion that goes through those graphs. The fact that there is no vertex renormalizations makes the Schwinger-Dyson equation of the 2-point functions to not depend on higher point functions. So you don't have an infinitor of equation like you usually have with Schwinger-Dyson equations. And that gives you a very natural truncation of the Schwinger-Dyson equations. Now, I can actually, at this stage, if you are mathematicians, you may forget completely the model, the physical model you come from. That's also why I'm not writing the action of this model. And just try to analyze those equations. Of course, it's always good to keep in mind that there is physics behind those mathematics, but let's a bit naively go for it and map everything to the Borel plane and see what happens. So if we make a Borel transform in A, the fine structure constant of the theory, and the classical approach to this problem is to expand the 2-point function in power of L. So you obtain the same type of expansion, but in the Borel plane. Then the renormalization group equations, it gives you an inductions on the gamma n, and this induction can also be mapped in the Borel plane, and you obtain also an induction on the Borel transformed gamma. Very nice. The Schwinger-Dyson equations is not so nice, sadly. You have also some non-linearities that can get nasty. Some coefficients arrive that are given in terms of derivative of Euler's gamma functions, ratio of gamma functions. Okay, but let's not worry too much about it. Before we really dive into this type of analysis, and I reassure you, I won't give the all details of the analysis because I don't think that's very interesting. I just will try to underline the main tools and the main ideas on how to prove things. I think before I do that, a decent question is why this model? Why should we care? Why did I bother doing this model that is not supposed to be very physical since it's exactly supersymmetric? Well, the fact is, it's very simple. It's a good toy model. It's just a nice model to start with. And first, supersymmetry really helps a lot. I already pointed out that since you don't have vertex renormalization, you have natural truncation of Schwinger-Dyson equations. You can deal only with one equation instead of a tower of equation. So it's much nicer. Another nice fact about supersymmetry is that the beta function is just the gamma functions times 3. So the renormalization group equation is actually fairly simple. So those two arguments tell you this is a good toy. But the fact is, it's also a good model because of this non-linearity in the Schwinger-Dyson equations. By non-linearity, I mean that you renormalize two propagator. And this is a very important feature of more physical models. It makes your life more difficult, arguably. In this case, it will make the algebra of singularities more complicated. That is not to say that if I had only one propagator, the singularities in the Borel plane would be trivial, not at all, but they might be simpler. So it's also a good model, and it also has many important features of more physical models. And I think those two arguments are why this model has been studied before. It was studied in particular by Marc Belon, Fidel Chapusnik, and myself with Marc. So the results that are known about these models is that first, this system of equations admit a unique solutions in terms of informant series, and that this solution is 1G with asymptotic induction relations on the coefficients. With Mark, we've also shown that the Borel transform is actually of the anomalous dimension is actually resurgent. So we know a lot about the anomalous dimension of the theory, and at least in principle, the renormalization group equation those information should be, we should be able to transfer this information to the full 2-point functions using the renormalization group equations and also the Schwinger-Dyson equation. So I started with this model because if I am not able to do this on this model where I already know so much, I don't think it's worth starting doing harder model, for me at least. So I use it as a crash test. This is if I can do Borel-Ecalle on that, it's good, and it's a good method to tackle this problem of resummation in quantitative theory. So let's see what we can do. Let me remind you that we need to prove 3 things. That my format series is 1G Vray. That's so functional factorial bonds at infinity. That its Borel transform is resurgent, and that it admits an exponential bond at infinity. The fact that it's 1G Vray is actually not very hard to prove. You write it as a format series in A. Then the renormalization group equation gives you solution. You can solve the renormalization group equations. The coefficients are actually polynomials in the external impulsions. You find the induction relation for those case coefficients. And the C numbers that you obtain are the coefficients of the gamma functions. Then, since you know that gamma is 1G Vray, you can use your induction relations to prove that this is also 1G Vray. It's a bit painful, but it's philosophically not really difficult. There is nothing amazing there. More difficult things, and I think the main difficulty of this program is to prove that this series is resurgent. So a first observation is that since we know that gamma 1 is resurgent, the anomalous dimension, we know for pretty much for free that they are all resurgent, at least in one direction. So why? Well, since we know by Ecalle and Sauzin that the convolution, that the algebra of resurgent function is stable under convolution, derivation, multiplication by integer functions, and so on and so forth, the renormalization group equations gives you for free by induction that all the gamma n's are resurgent. So all the parts that are in the 2-point functions are resurgent. The only things you have to check is that these series actually converge, where the right-hand side has to be understood as the continuation along any path that avoid your singularities. So what do you need? You need to start from a bond for gamma, which you know exists because you take for granted that it is resurgent functions. Using the renormalization group equation, you want to find a bond for gamma n. And well, I don't know how to do that. It's extremely hard. I don't know how to bond convolution products. But the miracle for me is that someone else knows, that Sauzin actually proved exactly the type of things I need. And I will try to not hide everything. So this is his difficult technical theorem. Let's not look too much into the detail and look just at the main results at the end. That the convolution product of n resurgent functions in a domain that doesn't go in distance at distance less than delta to the singularities, and in a with path that points that can be reached with path from the origin of length less than L. So the notation is not very happy here because L is not the impulsion anymore, it's a length. Sorry about that. Then this convolution product is bound by the product of the bonds of each of the terms. But there is a very big caveat there. This caveat is the bond that I have in the right hand side are actually not in the same domain on which I have for which I am able to bound the convolution product. So if I want to bound my convolution product on some domain, I need a bound on each of its component convolution product in a slightly bigger domain. You can see that L prime is slightly bigger. Well, it's not very difficult actually to see that delta prime is also slightly smaller than delta. So this makes your life difficult because the most natural things to do when you have the nice renormalization group equations that gives you formula for the gamma n inductively is to say I have a bond for gamma, so I found a bond for gamma 1 and by induction on gamma n, and I'm done. Sadly, it doesn't really work like that, because you will have to start either from infinity, on which you cannot really say anything with gamma, so that's not well, or you can actually generalize a bit this theorem so that you can play around with L prime and delta prime, so that you can start from somewhere close, but you have to the different domain becomes closer and closer to not being smaller. And at some point you have new divergences that appear and it just doesn't work so well. It almost works, but not quite. So instead of doing something smart, you go a bit more brute force, and I apologize, that's my worst slide. That you write that gamma n plus 1 is actually a differential operator to the power n applied to gamma. Then you can expand this differential operator into some terms that are indexed by words written in alphabet in 2 letters. And you can really a bit by brute force find bonds in terms of not only n, but also some intermediate initial functions. And then you can use Sauzin's result to bound this initial, the convolution power of these initial functions. So this is a painful analysis, but when you put everything together, you find this type of bond for gamma n, and you eventually find out that the 2-point function is resurgent, as you were trying to prove really hard. Okay, so that's really good. The last things to prove is the asymptotic bonds on the main, the principal branch.
Sorry, in the estimate before there was no delta.
Excuse me?
There was no delta anymore in.
There is one here. It does play a role. It still play a role. You still use it there, and those alpha, zeta, a zeta, b zeta, they are very complicated constant that involves everything there, in particular delta.
Thank you. Mm-hmm.
I'm also not going to give you details on how to prove these asymptotic bonds. Just one remark, that since you work in the principal branch, the principal branch is star-shaped with respect to the origin, so that instead of making a convolution product along very complicated path, you do it along straight lines. And so the bond for convolution products is much simpler in this branch, and that will really, really simplify your life. So the basic idea is to say you start from bonds of gamma hat and its derivative, and using the renormalization group equation, you found a bond for gamma n. Then you can plug this bond into the Schwinger-Dyson equations and you obtain some ugly functions that, as functions, you can study and see what its behavior is, and eventually you put everything together, you find that the Borel transform has this type of exponential bond. Okay, so putting those 3 results together, I obtained my main result, I guess, that the 2-point functions that solve the renormalization group equation, this meaning the solution of the renormalization group equation and the Schwinger-Dyson equation, is Borel-Ecalle summable. The resum functions solve, again, the renormalization group equation and the Schwinger-Dyson equations. And if you work explicitly the coefficients, m in this bound, you can find for which domain it is analytic, and it's a domain of this shape. So you have an analysis domain in this nice U. So this is I hope this kind of answered the questions of someone at the beginning. Of course, I have been fast on how does the proof works in detail, but I hope I have convinced you that at least it's doable and at least tools exist. So to conclude, what are we able to do with resurgence to attack the resummation of perturbative series? Well, we can first apply it in at least one nice quantum field theoretical case, which is non-trivial, I would say. And also, even if I did not really talk about that, it can be really used to compute non-perturbative contribution of physical theory, starting from the purely perturbative series, using really IAMP calculus and a lot of tools of resurgence theory. So the punchline, I think, of resurgence theory is resurgence theory allow you to reach non-perturbative informations from perturbative informations. And I think this is absolutely wonderful. Of course, from there is a lot of open questions. So let me list some. In this kind of talks where someone presents a toy model, they always end up by saying that—
Excuse me, just a question. Do you expect anything special happening at A equals 1/10L?
Not really. Okay. The point is, this is probably not an optimal bound. So I think the analysis domain is actually slightly bigger. And I do expect something special to happen in the maximal possible bound. And what I do expect to happen is that it has a pole, a simple pole there, because with Mark, but using really the trans theory approach, we argued that there is a pole in these functions, which we interpret as a mass. So we had an idea for a non-perturbative mass generation, which I think we should be able to see in this approach. The problem is that this approach essentially gives you an existence result and doesn't really tell you what give you precise information about these functions. Of course, it tells you you cannot have a mass in this area, which is nice. So yes, it's the holy grail. This type of approach is, of course, the Young-Mills theory and the questions of are they Borel-Ecalle summable? And with Mark, we agreed that probably not, but they might be accelerosummable, so you might need acceleration. This is really a long-term goal that I don't think is to be tackled in the following years. One question that has puzzled me for a few months is that we have those two approaches of resurgence, those two applications of resurgence to quantum field theory, but they don't really talk to each other. And I'd really much like to be able to draw a bridge between those two equations, no pun intended. And that would be to find a Watson theorem for trans theory and resurgent functions, or to be more precise, maybe one of the generalization of Watson theorem by one generalization by Sokal or Nevon-Lina would be really nice. A theorem that tells you if I have a functions that is Borel-Ecalle summable, then what I obtained for the Borel-Ecalle obtained via the Borel-Ecalle summation methods can be approximated by a trans theory with some analytical bound on the error of the approximation. That's what the Nevon-Lina theorem is, and that would, I think, be extremely interesting in this framework, because, as I said, the Borel-Ecalle resummation gives you an existence theorem, and trans theory gives you computational power. So it will allow you to relate those two, or at least to take some of the computational power of trans theory approach into the Borel-Ecalle resummation approach. Other questions, maybe less philosophical, is that at the end of the Borel-Ecalle resummation, I thought you have to take a well-behaved average, and I didn't specify which one I took. So very natural question is, how does the result I build depends on that? And there's a conjecture that it doesn't, that actually changing the average just amounts to changing the parameterization of your solutions. This conjecture is based by a result of Menu, where he did exactly that in one specific case. And he did find that it's the same solutions up to a change of coordinates, but that's one specific case. I don't even know really what is a reparameterization, what could be a reparameterization in most general case.
What do you mean by coordinates?
It's because he was really working in the framework of dynamical system, and there was a natural notion of change of coordinates. In this case, it doesn't exist. That's my problem. I suspect that it doesn't depend, the solution does not depend on which average you've chosen, but I don't know how it will change. Maybe it will just be a change of the A, change of variable. It could be, but I'm not sure. I don't know what this 2 is.
There is also another question in the chat. So when you say that the original divergent power series knows about the term beyond polynomial order, do you mean to say that the original series determines a resurgent function? A resurgent function determines a trans series, whence the original series has a preferred completion to a trans series.
It has a preferred completions. Then you can ask, is this completion everything? Well, it might not be, but that I found a bit difficult to believe. But at least some part of non-perturbative physics is encoded into the perturbative approach. And yes, it does has a preferred transitory completion, which is essentially unique, I think. You don't really have choice on what you have to do, how you have to complete your perturbative series.
Well, no, in some nonlinear differential equation or even linear differential equations, the real part of the trans-series parameter is not fixed. Like, you're not looking for a single solution, so you might have a family of solutions, and that's completely unfixed by the perturbative data.
Yeah, yes. No, you're right. I'm probably getting carried away. You may have to have more initial conditions in some sense to fix some free parameter. You have this. I guess the Stoke constant cannot really be determined, something like this. Yeah, that's true. You're absolutely right. Absolutely.
And the definition of preferred factor is for resurgence? Or some other characterization?
Preferred factors? I'm not sure which preferred factors. There is in the completion of trans series, there are some free numbers that arrive and that are difficult to compute, or sometimes cannot be computed. And so you have some freedom, but I don't know if that are the preferred factors of the question.
Okay.
No. Finally, yes, I would really much like to characterize this Borel-Ecalle resum functions. Say, does it have singularities poles, as I said before? Or it's a real function, so I want to estimate it somewhere. And of course, Watson Neven-Lina theorem could be a way to do this. I think I am actually slightly over my time. I apologize for that. So I will just thank you all for listening to me, and yeah, if you have questions.
Well, thank you very much. So thanks a lot for a great talk. Let me unmute everybody so we can clap. And now we can ask questions. So I'm going to mute everybody again, but everybody has the possibility to unmute themselves. So Pierre, you should not forget to unmute yourself immediately. And there's already a few questions in the chat. So first question, you always end up with an analytic function, right? How does this work in case where analyticity is not expected?
You mean, I'm not sure what that could be. So you start with a formal series and you want to resum it, but to a function that is not smooth. That don't think this approach would be the right one then. What happened is that you always build a function that is analytic in a small domain of the complex plane. Of course, what it is outside of this domain, in general, it will have singularities, but I don't think you can.
Yeah, sorry. So maybe I can be more precise. So, for example, for QED, right, there's this argument by, I think, by Dyson saying that it shouldn't be analytic in the coupling or fine structure constant because it doesn't make sense if you put the negative value. So then somehow you shouldn't, at least at zero, you shouldn't be able to construct it as an analytic function. So then you get something, okay.
It's analytic in this domain, not around zero. And that's also what happened in the Borel.
So you shift the point where you're
Yes.
where you're developing somehow in the.
Exactly.
Okay.
Exactly. And typically there is a singularity at 0.
Okay.
You can, or at least it does not extend in the other direction.
Okay, thanks.
Another questions. How many singular directions are there in your model?
2 in the positive real axis and negative real axis. I don't really care about the negative real axis because I want to resum in positive value of the complete constants. We showed with Mark that there are no other singularities. It's much simpler than other physical models that have more singular directions. When you have more than 2 singular directions, you can have very complicated phenomenon where 2 singularities, well, of course, 2 singularities create another one in a third singular directions. And it's people like Schiappa and Iseto, Dorigoni, their students, they know that they deal with those type of problems that do appear in physics.
Are there further questions? I don't see more questions in the chat, or somebody wants to say something, to ask a question directly. No. Well, let us thank Pierre again. And
Thank you.
thank you.